Good morning, everybody, and welcome to the Royal Swedish Academy of Sciences and this press conference. The Academy met in session this morning to award this year's Nobel Prize in Physics, and we are now ready to announce it. My name is Göran Hansen. I'm the Secretary General of the Academy, and with me on the podium today are two members of the Nobel Committee for Physics. On my right, Professor Mats Larsson, who is the chairman of the committee, and on my left, Professor Ulf Danielsson. And as usual, I will read the announcement, first in Swedish and then in English. I will also read the citation in German, French, and Russian. Mats will make some remarks about the Nobel Prize, and Ulf will introduce the science behind the prize. And after that, we hope to have one of our new Nobel laureates with us on a phone line, and there will be opportunities for questions. Ready? This year's prize goes for contributions to our understanding of the evolution of the universe and Earth's place in the cosmos. Årets pris belönar bidrag till vår förståelse av universums utveckling och jordens plats i universum. Kungliga Vetenskapsakademin har idag beslutat att utdela 2019 års Nobelpris i fysik med ena hälften till James Peebles för teoretiska upptäckter inom fysikalisk kosmologi. Och med andra hälften gemensamt till Michel och Didier Queloz för upptäckten av en exoplanet i bana kring en solliknande stjärna. The Royal Swedish Academy of Sciences has today decided to award the 2019 Nobel Prize in Physics with one half to James Peebles for theoretical discoveries in physical cosmology, and the other half jointly to Michel and Didier Queloz for the discovery of an exoplanet orbiting a solar-type star. Zur einen Hälfte an James Peebles für theoretische Entdeckungen in der physikalischen Kosmologie und zur anderen Hälfte gemeinsam an Michel und Didier Queloz für die Entdeckung eines Exoplaneten im Umlauf um einen sonnenähnlichen Stern. Pour moitié à James Peebles pour des découvertes théoriques en cosmologie physique, et pour l'autre moitié, conjointement à Michel et Didier Queloz, pour la découverte d'une exoplanète en orbite autour d'une étoile de type solaire. À James Peebles za teoretические открытия физической космологии и à Michel и Didier Queloz за открытие экзопланеты на орбите вокруг солнцеподобной звезды. And here you have some biographical data about our new Nobel laureates on the screen. James Peebles was born in 1935 in Canada, in the state of Manitoba. And he has had his career largely at Princeton University, where he is today the Albert Einstein Professor of Science. Michel was born in 1942 in Lausanne, in Switzerland. He is Emeritus Professor of Astronomy at the University of Geneva, Université de Genève in Switzerland. Didier Queloz, finally, was born in 1966 and is also from Switzerland. He's currently Professor of Astrophysics, both at the University of Geneva and at the Cavendish Laboratory of the University of Cambridge in the United Kingdom. And I would now like to ask Mats Larsson, Chairman of the Nobel Committee, to make some remarks about the Nobel Prize. Mats, please.
This year's Nobel Prize in Physics deals with groundbreaking discoveries about our universe. The last few decades have brought remarkable progress in our understanding of the development of the universe and Earth's place in it. Cosmic background radiation was discovered in 1965 and turned out to be a gold mine for our understanding of how the universe developed from its early childhood to the present day. Were it not for the theoretical discoveries of James Peebles, the wonderful high-precision measurements of this radiation over the last 20 years would have told us almost nothing. His discoveries are rewarded with 1/2 of this year's Nobel Prize. In October 1995, Michel and Didier Queloz announced the discovery of an exoplanet orbiting a solar-type star. This was a revelation that forever changed our view of the Earth's place in the universe. Since then, more than 4,000 exoplanets have been found. Recently, Earth-like planets with the potential to host life have been discovered. Professor Ulf Danielsson will now describe these exciting discoveries in detail.
Tack så mycket. James Peebles is awarded the Nobel Prize in Physics for discoveries in physical cosmology. The whole universe was in a hot, dense state. Then nearly 14 billion years ago, expansion started. We don't know what happened before then, but after a little less than 400,000 years of expansion, the universe had cooled down to a temperature of a few thousand degrees and become transparent to light. We can, using our astronomical instruments, look back to these ancient times and study the cosmic microwave background radiation. At that time, when light lost its grip on matter, galaxies started to form. But it's only 5% of the energy in our universe which is in the form of ordinary matter like stars and planets and living beings. 26% is in the form of the mysterious dark matter. 69% is the dark energy that forces the galaxies to move away from each other ever faster. We are living towards the end of the era of the galaxies. Over the next several billion of years of expansion, our universe will turn into a darker and lonelier place. One can compare our universe to a cup of coffee. Most of it is, of course, coffee. This is the dark energy. Then a fair amount of cream. This is the dark matter. And then just a tiny little bit of sugar. This is the ordinary matter. This is what science has been all about for thousands of years.
Thank you.
Up until now. This is the picture of our universe. Looking back almost 14 billion years in time, this is the cosmic microwave background radiation. Already at the time of its discovery, in the mid-1960s, James Peebles realized the importance of cosmic radiation. Over the next 2 decades, he developed new theoretical tools and used them to uncover the dark components of our universe. Through his work and new ways to observe and measure our universe, cosmology evolved into a science of precision. Science of precision based on the mathematical foundation. Cosmology matured into physical cosmology. Michel and Didier Queloz focused on what is most important to us, the sugar in the cup. They are awarded the Nobel Prize in Physics for the discovery of a planet in orbit around another sun. They studied an anonymous star 50 light years away, visible to the naked eye under dark and clear skies, in the constellation of Pegasus, the flying horse. They couldn't see the planet directly, so they had to use other methods. When a planet is orbiting a star, the star wobbles back and forth. In the same way as the sound of an approaching train changes its pitch when the train moves towards us and then away, there is a subtle change in the color of the star. As the star moves towards you, the light gets a little bit bluer. When the star moves away, the color is shifted towards the red. The effect is tiny, and you need care and ingenuity if you want to detect it. This is the result. This is the discovery of the first planet in orbit around a solar-type star other than the Sun. The planet had unexpected properties. It was so close to its Sun that its year lasted no more than a few Earth days. Its temperature was 1,000 degrees, and it was as big as Jupiter. Few had expected that such planets could exist. We had thought that other solar systems would be similar to our own. We were wrong. We now know there are many different kinds of planetary systems. In our own galaxy, our own Milky Way, there might be billions of planets. Some of them might be similar to our own Earth. Through the study of these exoplanets, we will learn more about the physics of how planets form and evolve, and get a new perspective on our planetary home. This year's Nobel Laureates in physics have painted a picture of a universe far stranger and more wonderful than we ever could have imagined. Our view of our place in the universe will never be the same again.
Thank you, Ulf. Thank you very much. Now we hope to have one of our new Nobel laureates with us on the phone line. Let's see if it works. I'll get the magic signal here if we have connection. Yes, Dr. Peebles, are you there?
Yes, I am here.
Yes, hello. This is Göran Hansen again. I'm the guy who woke you up, I suppose, an hour ago or so to give you the good news.
Yes, you did.
Yeah, sorry about that.
Well, it's all right.
So we're having a press conference right now here at the Royal Academy of Sciences, and we have a large number of journalists here. I'm sure they would like you to ask you some questions. Are you ready for them?
Willingly, yes.
Who would like to start? Thomas von Heine.
Good morning, sir. Congratulations.
Good morning.
This is
Thank you.
Swedish television, public service television. I'm curious because Professor Danielsson just showed us the image of the universe where only less than 5% is actually matter that we can detect. What's your take on the other 95%? What is dark matter and what is dark energy?
Isn't it fascinating that we have a very clear evidence that our universe did expand from a hot, dense state? But yet, although the theory is very thoroughly tested, we still must admit that the dark matter and dark energy are mysterious. It means that although we've made great advances in understanding the nature of evolution of our universe, there are still many open questions. In particular, as you ask, what in the world is this dark matter and this Well, it's Einstein's cosmological constant. You know, it is so ironic that Einstein introduced the notion of what we now call dark matter, earlier called Einstein's cosmological constant, and you know the name of the name change was simply, didn't mean anything. We still don't know what it is. But ironic that Einstein saw a place for this cosmological constant or dark energy in his equations. He put it in, then decided it's ugly, took it out, and now we put it back in.
Indeed. More questions to Dr. Peebles? Please, lady over there.
Hello, my name is Anneli Midmer Arn. I'm from Swedish TV4, our private TV channel. 14 billion years, you look back that long upon our universe, and I think I have to ask you the most fundamental question. Do you think there are life on other planets?
This, of course, is only a guess. And it is remarkable, ironic, that we could be very sure that there are many planets, and among them, surely some will be suitable for life of some sort. And surely, I think, on some of those planets, there will be something we might be willing to call life. Whether it would be at all like life on Earth, very difficult for me to know. Perhaps chemists will sort it out. Ironic that we have this vision of life on other planets, and we can be also very sure that we will never, ever see these other lives, these other planets. It shows the limitations, the great advances in science, the great power of science, and the great limitations.
Thank you. Gentleman over there with the camera up on the platform. Here we go.
Thank you very much. David Keaton from the Associated Press. Sir, first of all, congratulations. I would like to know how you felt this morning when you received the phone call from the Academy, and also this part of your prize is for theoretical discoveries. How does it feel sharing this prize for the more practical applications of this, and how do you feel about the sort of like the this interaction between theoretical and practical discoveries?
It is so important that there is that interaction. Theory in any of the natural sciences is empty without observation, in my opinion. You recall that the establishment that our universe is evolving was in part a theoretical discovery, but that was meaningless without the evidence, the very firm evidence now that it really did expand from a hot, dense state. We depend on that interaction of theory and observation. And of course, in finding our way through the nature of our world, the discovery of planets was extraordinarily exciting. The discovery of a planet around a star like the sun is exciting. That will continue. Astronomy is not running out of food, and I can't imagine it ever will. So many stars nearby, so many to examine to see the sort of planets they contain, and of course so charming to me to think, because I've lived a long time in this field, that we had a pretty good theory of how planets form until the first extrasolar planet was discovered. That's a good illustration of the nature of science, isn't it?
Thank you. Yes, the lady over there. You'll get a microphone in a second.
Hey, James. Congratulations for getting this year's Nobel Prize in Physics. This is Nordic Chinese Times. And my question is, have you ever thought you could be awarded such a big prize in the world when you conduct your research? And also, if possible, can you share some advice to the young scientists nowadays for us to finding more discoveries in the universe or even in the medicine and everything? Thank you so much.
Thank you. Of course, I had, when I started working in this subject, I can tell you the date, 1964. At the invitation of my mentor, Professor Robert Henry Dickey, I was very uneasy about going into this subject because the experimental observational basis was so modest. But I could think of one or two things to do in cosmology, and each of them suggested something else, and I just kept going. Never a plan of great discovery. When the observations started catching up with the theory, I was, at regular intervals, startled at the great power of advances in technology to test these ideas. So a thing of this sort, I think, very seldom can be at all conceived or planned. These things just happen. I do have advice to young people entering science. You should enter it for the love of the science. The awards and prizes and awards, well, they are charming, very, very much appreciated, but that's not part of your plans. You should enter science because you are fascinated by it. That's what I did.
Very good advice indeed. Yes, question over there.
My congratulations, James Peebles. My name is Joanna Rose. I am from Nobel Media. I wonder, what would you view as your greatest insight in cosmology?
I've read that often winners of major prizes are a little uneasy about the nature of the statement of the award because they feel that it was slightly off. I have no such feelings. I've lived a very long time. You know, 1964, when I started working, is 55 years ago. Where did all that time go? I might also remark, we should put this in the context of the fact that Einstein in 1917 put the first starting ideas along the direction of how we have gone in cosmology. That's a little over a century. I've been working in this subject for over half that century. Progress has been slow, steady at first, halting at first, increasingly speeded up. Which particular step did I take? I would be very hard-pressed to say. It's a life's work.
Thank you.
And well, may I add,
please.
I was not working alone. The field, of course, was small until the 1980s, when people started to notice the power of what could be done. But always, from the beginning, I had colleagues. Particularly notable, and I think I ought to say it, is in the Soviet Union, there was a remarkable physicist, Jacob Zeldovich, who, after the Second World War, became interested in cosmology and made signal contributions and generated a group of others who made signal contributions. I was a postdoc, a graduate student and a postdoc, and a colleague of Robert Henry Dickey here at Princeton. A similar story, he founded a group. That group is still in operation. We still call it the Gravity Research Group, or at least I do. These people were working along with me, and although I have an iconoclastic turn of mind, and so many ideas were put out. I put out lots of wrong ideas too, you know. The subject grew, and I grew with it.
Thank you very much. I think we'll move on. So thank you very much again, Dr. Peebles, for being with us today, and we look forward to greeting you here in Stockholm in December when you come to receive your Nobel Prize. Thank you.
Thank you.
Bye-bye. So now there's opportunities for questions to the panel. Everything was crystal clear. I also thought that Daniel's presentation was exceptionally good.
Okay.
And Mats initiating remarks as well. Any questions to the panel? If not, I know that you're eager to make interviews now with experts, so I think we'll close the press conference, and thank you for your interest, and I hope to see you back tomorrow for the Nobel Prize in Chemistry. Thank you very much.
Professor Ulf Danielsson, member of the Nobel Committee for Physics. This year's Nobel Prize is twofold. So let's start with the first part about the universe. What did you award?
Sorry?
What was the award about?
The award was about really this discovery of the universe, in a sense, the whole history of the universe and the contents of the universe. And James Peebles is one of the most important cosmologists of our time, and he has contributed to several really essential pieces in this puzzle. So it's about really to realize what our universe consists of. It's not only ordinary matter, the thing that we sort of experience in our daily life, but there are also other unknown dark components. 95% of the energy of the universe is really basically unknown. We just know some of its properties. That is the dark matter and it's the dark energy. And James Peebles have revealed how, by looking back in time towards the Big Bang, looking at the cosmic microwave background radiation which had been traveling to us for almost 14 billion years, how you in that radiation can read off basically the contents of our universe.
That is mostly unknown.
It's mostly unknown. We know the properties, the general properties of this. The dark matter is sort of like matter. It's in clump and it can form gigantic clouds around the galaxies. We know it's there through its gravitational influence on other matter, and also in the early universe when the dark matter had to be there in order for galaxies to form in the first place. But we don't know what that dark matter actually is. And then there is the dark energy, which doesn't really clump. It's spread uniformly through the universe, but it has the property of accelerating the expansion of the universe. So the galaxies are moving ever faster away from each other, but again, we know it's there. We know that it dominates the energy of our universe, but again, we don't know what it actually is.
What metaphor would you use to describe the universe?
Well, one metaphor that I really liked, which I also used in the presentation, is to compare with a cup of coffee. Then, I mean, most what you have in the cup of coffee is, of course, the coffee itself. That's the dark energy. I think that's a very nice parallel. Dark energy, that's the coffee in the cup. But it's not only that. You also need to have some cream or milk. Quite a lot. Not as much as the coffee, of course, but still a fair amount of that. That's the dark matter, like a quarter or so. And then just a tiny little bit of sugar. That's the ordinary matter. That's what makes the universe sweet, in a sense. That's us. That's the stars. That's the planets. And then you have to stir a bit, and that's your universe.
And in this sweet universe, we have planets.
We have planets, indeed.
That takes us to the second prize, part of the prize. What was it about?
That's about the discovery of the first planet in orbit around a solar-type star. So it's really the first planet which you could sort of compare with our own solar system. It's sort of the first example where we're really trying to see how does other solar systems look like. So the star in that system was very similar to our own sun. But the big surprise was that this first other planetary system was so different from our own planetary system. We had thought that all planetary systems would sort of look the same, like our solar system. But in this system, it turned out that there was a big planet, as big as Jupiter, but it was so close to its sun that it took just a few days for it to go one orbit around the sun, while Jupiter takes like 12 years and the Earth obviously 1 year. So it's extremely close, which means that it's also very, very hot. So it's a solar system, a planetary system, very different from ours. And since this first discovery, one had discovered many different kinds of planetary systems. So it's a very rich and varied universe out there, full of planets, actually. I mean, there might be billions of planets in our own Milky Way.
And why was it so hard to find if it was so big, the first planet?
Well, the planet is big, but the universe is also big, and stars are quite big. So it's, first of all, a planet that close is very, very difficult to see because it's hidden in the light of the star. On the other hand, it's easy to see because it's close for another reason. And that is that the planet is certainly orbiting around the star, but the star is also moving a little bit. They're moving around a common central mass. So the star is also wobbling a little bit back and forth. And then if you look at the star and carefully measure its color, there are techniques to do that, you can see that the star is actually moving back and forth along the line of sight. And if you can measure that, then you can calculate the effect of a planet. And you can see that it's a planet which is doing that. So through that wobbling motion, you can detect the motion of a planet around the star. That was the technique used in this particular case.
So you actually don't see any planet?
You don't see the planet, you just see the effect of the planet. Then since then, there are other methods which have been developed, where you instead look at the star, and then if you're lucky, the planet will be orbiting in front of the star, and then you can see a little bit of a dip in the light curve. And this is a method which has been used over since then to discover a large number of planets. So there are basically these two different methods to detect planets, but in neither of them you directly see the planet, just its effect on the light from the star.
Do you think we will ever find life outside there in the space?
Well, I would say that these kind of discoveries now is certainly a step on the way to figure out how it really is, if there is life or not. We now have a chance to actually not just speculate, but go out and observe and try really to establish how it is. Because in the future, and it might be actually quite near future, we will be able to, particular perhaps with planets which are moving in front of the stars, we could be able to measure and detect the atmospheres around such planets, and then to see whether there are, what kind of gases there are, whether there are oxygen or water, vapor, and so on and so forth. And in this way, we could take further steps to see whether there actually is life out there. Me personally, I think there is somewhere.
Let's talk a little about the Nobel laureates. Michel and Didier Queloz are the two who get the prize this year. Did they work together, or did they
work together on this particular discovery? So they are really, it's a joint discovery with these two scientists. So there is a key paper where they discuss this discovery, and that is these two together.
And finally, my question would be, if you had 30 seconds to say, what makes you most excited about this year's Nobel Prize?
I think it's really a common theme in both these prizes, because they really sort of tell us something very essential, existential about our place in the universe. I mean, the first one, the Cosmology, the history back to an unknown origin, so fascinating. And the other one, I mean, it tries to answer these questions about, are we alone? Is there life anywhere else in the universe? It's really about our place in the universe, both of them.
Thank you, Danielson, for taking your time.
Thank you.